Thank you, Fabrizio and Marco. It's great to be back, and thank you for organizing this conference. It's been really excellent talk so far. And we today want to talk about the concept of hierarchy in neuroscience, or specifically systems neuroscience. And talk of hierarchy is sort of found across many different parts of neuroscience, but unfortunately, there's almost no philosophical analysis of this concept. And we think that's unfortunate because there's a variety of connotations or senses of the concept hierarchy with distinct commitments that should be fleshed out. And they sometimes also get conflated within the literature. And these different senses arise because researchers use multiple different approaches with overlapping but not identical tools to measure hierarchy in the brain. So for instance, they use layer-based anatomical histology methods or graph theoretical measures to describe the brain as a hierarchical system. And our question today is whether these different approaches to hierarchy fit together. And we are going to distinguish broadly two approaches to the concept of hierarchy. One that we simply term traditional approaches that usually are committed to the idea that there are very specific anatomical connections in the brain that underlie a hierarchy of discrete representations and routing of representations along this sort of processing hierarchy in the brain. And the paradigmatic example that's being used there is usually the visual system. So here's an example of the ventral processing stream in the visual system, which Kravitz et al. Describe as containing representations of object quality. So that's the sort of idea that there is a hierarchy in which the representations of object quality is being elaborated from simpler to more complex. And in contrast to these traditional approaches, there are a number of approaches that we call simply novel approaches that focus more on the topology of the brain as a network and on the diversity of different connection properties within that network. And these approaches, we claim, are not committed to specific representations at each level of the hierarchy, but only to the idea that different parts of the hierarchy have different roles. So a node in the network could be part of a module, or it could serve integration functions by being part of a short path throughout the network, or it could form a region of hubs that are themselves interconnected, such as in this example above. And there's no claim about the representational function involved in these topological descriptions. So let's start with these traditional approaches. And the backbone really here is the idea of anatomical hierarchy. So the idea that we can analyze the brain as an anatomical network. And what's usually being done is that we start by characterizing brain regions in terms of their connections, and we interpret these connections as the inputs and outputs to an area. And once we've had these sorts of data, we can use a hierarchical analysis. Here on the right is a very famous example of Velleman and Van Essen, in which they sort areas or connection patterns in areas depending on whether they're ascending, which means that they have origin connections in the supragranular layers, and then forward to the supragranular and infragranular layers, or whether they have lateral connections, or whether they have descending connections between an area. And so once we classify areas in terms of their descending, lateral, and ascending laminar patterns, we can sort them in sort of into a hierarchical order. And that's exactly what Velleman and Van Essen did in this famous 1991 paper, where they used these connection data, histological data on the macaque visual system to produce a hierarchical diagram describing the visual system. And that diagram, as I will show you in a minute, involves a hierarchical sense of level in which an area receives input from ascending connections and sends its output through the descending connections, and areas at the same hierarchical level are characterized by mainly lateral connections. And Fellman and Van Essen used this definition together with their classification to produce this famous diagram of the macaque visual system, which consists of different levels, starting from the thalamus and then going into V1 and going up to the frontal eye fields and higher visual areas. And what this already showed here, this functional architecture that has been shown here, is that the visual system is in between a serial and a random network, so that it has sort of properties that fall in between these two classes of a network. Now, usually this anatomical hierarchy is functionally interpreted as implementing what's called a processing hierarchy, or what we call a processing hierarchy. So here the idea is that there are not only inputs and outputs from one region to the other, but that these inputs and outputs determine which features an area processes. So depending on what input it gets, that's the features that it processes, and that it can feed forward along the hierarchy to other areas. So the functional architecture as depicted in this diagram would be that we start by regions in the visual cortex such as V1 that process relatively simple features such as the orientation of the stimulus, and that these representations are then fed forward into higher levels of the hierarchy where they are used to build more complex representations such as representations of the face. And because there is this sort of dependency of lower level representations to higher level representations, the latency time along this hierarchy, along this processing hierarchy, increases. Or at least that's an implication of this view. And although most neuroscientists discuss concepts of hierarchy in paradigmatically in the visual system, this view of a processing hierarchy has been extended to the entire cortex. So the idea here is shown a famous model by Mesolam is that we start with primary sensory areas at the sort of first concentric ring here of this hierarchical diagram, and then through connections, these will first process one sensory modality, but get subsequently integrated by cross connections into multimodal representations, and therefore the abstraction of the representation will increase along the hierarchy, which means that the representation builds on multiple modalities and will be more invariant to variations in the stimulus. So that's the roughly the view of the traditional approach, how hierarchy, the concept of hierarchy applies to the brain, or at least the cortex. In contrast, there has been a variety of new techniques from graph theory that have been used extensively in the last 2 decades to also characterize the brain as a hierarchical network, but based on sort of graph theoretical definitions that can be used to spell out this concept. So the first question that you can ask is how many connections does, so graph theory represents the brain as a network of nodes and edges, and then once the edges would be interpreted as the connections between the nodes, for instance, axons or fiber bundles. And then you could ask, well, given a specific node, such as a brain area, how many connections does it have? And that is called the degree. And the idea is here, the higher the degree, the sort of more central the node is to the whole network, because it connects many different nodes. Another more complicated measure that you could use to determine hierarchy is called betweenness centrality. So here you ask how many of the shortest paths that run through the network, such as here along this route, run through the given node. So if there are many short paths that run through the given node, it means that it connects many different parts of the network along the shortest path, and that therefore it's central for connecting different parts to each other. And then finally, we could use these measures to define hubs in the network, such as shown here below. And those are nodes that have both high degree and, for instance, between the centrality, if there are these connector hubs that connect many different modules in the brain. And based on these definitions, these graph theoretical definitions, we get a sense of hierarchy or of hierarchical level that scales with these measures of centrality of a node with respect to the entire network. And so one way to operationalize this hierarchical sense of level would be what Sporns and DaCosta did here in this diagram, to look at the degree distance. So if I pick out a reference node, I can ask how many connections do I have to pass, or how many nodes do I have to pass to get, for instance, from 5 to 1. If I have to pass 2, there's a difference in hierarchical level of 2 between these, and there's a distance between 1 if there's only like 1 connection in between. And that will be one operationalization of hierarchical level in terms of distance of degree. And the functional architecture that is being revealed by using these graph theoretical measures is, for instance, if we look again at this the Costa and Sporn study, a difference in different parts of the macaque visual system again. And here they used 4 different measures of hierarchy to get some sort of hierarchical fingerprint of different areas. And what they revealed is that, for instance, here on the left, you see that brain regions in the dorsal cluster of the visual system connect to nodes on hierarchical level 1, which is shown here, for instance, for V2 or V4 by these white triangles or like parts of the circle here in the middle. That's hierarchical level 1. And in contrast to that, in the ventral cluster, we see that they more connect to nodes on hierarchical levels 2 and 3, which are these outer layers here, and then you have here these white fields that show maximum values in these hierarchical measures. Now, these graph theoretical notions are static, measure static properties, but they have implications for the dynamics of the system, because they basically measure how a signal would spread from that node when it gets activated. And one way to make this sort of dynamic implication explicit is to focus on temporal hierarchies within the topological framework. And one concept here that would be interesting to sort of make this explicit is called, or has been introduced by Deko and Kringelbach, called intrinsic ignition, which refers to the capability of a local node to propagate feed-forward and recurrent activity to other network nodes. And once we have this sort of concept, we can define events in our time series of neural activities. So for instance, here is shown fMRI signals in different brain areas. And once we find such an ignition event, which we can look at or see here by the onset of co-activation in different brain areas, we can ask for the intrinsic ignition capability of a brain region by measuring integration. And integration here means that we look for the largest subcomponent in the connectivity matrix of these different time series, a binarized version of that, and search for this largest subcomponent. That's basically the component of the network that's being integrated by this ignition event. And the important part here is why it's an intrinsic ignition event is that it can apply both to resting state data or task data, so that it's sort of more general. And the idea here is that the integration value measures the degree of broadcasting a signal throughout the network. So the idea is the higher the integration value, the higher the position of that area or that intrinsic ignition event within the hierarchy. And that's a dynamic notion of hierarchy here. That's still based on this topological notion. And if we look at studies that sort of look at the temporal hierarchy from this in these novel approaches, the functional architecture that seems to emerge is that we have a graded but non-uniform hierarchy, for instance, of these intrinsic ignition values. So there's no strict discrete boundary between different hierarchical levels, but more of a gradient. And that has been also shown by an independent method used on functional connectivity data in fMRI, where we look for the greatest variance in functional connectivity values. And there, the study by Margulis et al. Has found that the two largest components in variance run from here first primary sensory areas up to default mode network areas, and the second gradient distinguishes different primary sensory areas from one another. And what we think, what one can see from these studies is that there is not a strict commitment to the representational function of each level in the hierarchy. And the first thing to note here why this is the case is that if there are functional interpretations given of these new network analyses, they're usually derived from assumptions that are not directly built into the graph theoretical measures themselves. So they're sort of like a theoretical background or a conceptual background against which they are imported to interpret the studies, but they're not part of the analysis technique themselves. And that's also a view that has been explicitly, for instance, acknowledged by Da Costa and Sporns, who write that their goal was not to identify unique hierarchical arrangements of brain regions in terms of processing stages of the streams, the visual streams that they were looking at, but they simply focused on the causal effect or the spatial temporal propagation structure of the signals in the brain as a network. So here, hierarchy is not tied to or is neutral with regard to the specific representations that areas process or compute at different levels of the hierarchy, which is a commitment of the traditional view. And with that, I will hand over to Dan, who will now talk about the implications of how these two approaches relate to one another.
Okay, good. So just to kind of summarize what Philip said, so we have these two pictures that we're looking at. One is the idea that there's a relatively strict anatomical hierarchy, and that this underlies a relatively discrete representational hierarchy, such that simpler features, unimodal features are represented at lower levels of hierarchy, and more abstract, ultimately multimodal features are represented at the higher levels of the hierarchy. And ultimately, this picture is supposed to continue into things like frontal cortex, where maybe action plans or rules are represented, utilities, values, etc. On the other hand, we've got the topological hierarchy and temporal hierarchies, which are based on notions of patterns of connectivity between different parts of the brain. And what we've said is the key thing about that is that there's no commitment intrinsic to the measurements themselves about the representational role of the different levels of the hierarchy. So there it goes. So these multiple distinct senses of hierarchy, all of which invoke different notions of level. And the question is just, how do these different views map together? Now, the most natural view is, for many people, the most intuitive view is what we'll call the substantiation view. I want to pause for just a moment to really stress this idea of a anatomically underpinned processing hierarchy, especially based on the model of the visual system, is extremely, extremely influential. So many people take this to be the sort of the exemplar for understanding of organization of systems in the cortex. And because of its widespread influence, one temptation a lot of people have had in looking at the graph theoretic approaches is to say, well, this is a way in which or this is an expanded view of the anatomical underpinnings of the processing hierarchy. So basically this takes the measures given by the graph theoretic notion to substantiate the traditional functional view that we've always had. And there's a couple of reasons for this. One is the notion of a module. So the notion of a module is often interpreted as an area that's functionally specialized to serve certain purposes. Another thing that is often elicited in support of this is the idea, or the empirical fact that hub areas, so areas that have high centrality, are often in alignment with areas that were posited to be higher up in the traditional hierarchy. So instead of being in unimodal cortices, hub areas are often in frontal cortices, parietal cortices, anterior temporal cortices, areas that we've always taken to play integrative roles. The other is the fact that there are groupings that do align with the notion of a hierarchy. So this is some data, or the diffusion model that Philip showed you earlier from Margulies et al. And basically what this is a dimensionality reduction. It's not PCA because it's not linear, but it's basically a dimensionality reduction device. And basically what they did is they took the functional connectivity matrix and they asked what dimensions they could use to describe the variance in functional connectivity. And basically what they did is they showed that there are two primary axes or gradients. And one showed that areas in the brain that have always been known to be multifunctional, like the default mode network, were at one end of the gradient, and traditional primary sensory and motor cortices were at the other end of the gradient. So now there's a gradient which captures some of the intuitive structure of the cortex. And similarly, the second gradient distinguished along primary modal cortices and motor cortex. So I have to apologize, it's already past 11 p.m. in Australia, so stumbling a little bit. You'll notice that the way they choose to represent these gradients is almost exactly the way that Mesulem chose to represent the traditional hierarchy view, which we showed a number of slides ago. But what's important to note here is that they're choosing to represent this in the same way as the traditional hierarchy is represented, is nothing that falls out just of the analysis, right? This is just an analysis of connectivity. The analysis itself has no upshot for the representational role. You might choose to read into this that these areas are in charge of representing more abstract information, representing rules, representing goals, that sort of thing. But it's nothing that falls out of the connectivity pattern. Okay, so stemming from that, the second option is to go the other way and say, well, look, the traditional processing hierarchy and the topological hierarchies just invoke very different notions of levels. To the extent that there's data that can be incorporated by one as opposed to the other, we might actually take these two different kinds of hierarchy to be in conflict with each other. And you might even think, if you're of this persuasion, that the topological hierarchy will come to replace traditional hierarchies. So one data point that we think is particularly troubling for the traditional hierarchy view is the area V4. So area V4 is layer 6, I believe, in the Feldman and Van Essen's hierarchy. And what that suggests is that it should play a very well-defined representational role. Also, that its activation should follow the activation of areas earlier than it in the hierarchy, and should precede the activation of areas later than it in the hierarchy. But what Capalbo et al. Did was they just looked at latency. So how long does it take information about a visual stimulus to reach a particular area of the visual cortex? And what was really interesting about this is that V4 actually has the longest latency. Its latency is longer than areas that are after it in the traditional hierarchy. So this is a data point that we take to be in conflict with this idea of a serial processing hierarchy, because if that were true, then V4 should be earlier than these other areas. Similarly, it turns out that according to both degree and betweenness centrality measures, closeness is a related measure. But let's just look at these two. According to these two measures, V4 is actually at one of the highest hierarchical levels of the entire brain. So let's think about this for a minute. According to the traditional view, V4 is at a very low level of the hierarchy within unimodal sensory cortex, but by the topological measures, it's actually one of the highest levels of hierarchical levels in the brain. So we take this to be, again, a data point against the traditional view. Moreover, physiological data actually suggests that there's not a very clear abstraction gradient in representation after all. So this is data from, amongst others, David Van Essen, who was one of the original progenitors of the traditional processing hierarchy view. And what Hegde and Van Essen did in 2007 was they said, well, let's actually test this. Let's look at very simple gradings, slightly more hyperbolic figures, and then complicated polar or radial figures, and look for differences between V2 and V4. And what they actually showed is that there's very little difference at all between preference for these more complex figures in V4 versus V2. So unlike what the traditional hierarchy view says, the more complicated features are not represented solely at higher levels of the hierarchy. There were some differences, but they were differences of degree and detail. They did not match into any difference about complexity of the stimulus that V4 represents as opposed to V2. So we take there, at least in this case, to be a relatively significant amount of data that the topological hierarchy just doesn't match the traditional processing hierarchy. And if that's the case, then we should be worried about this substantiation view. We might actually think we need to take the topological view as an alternative. Finally, you might be a pluralist. And there are a couple different ways to be a pluralist. So you might look at these different concepts and you might say, well, okay, they're just different concepts. They're not really in conflict with each other, but we also shouldn't expect the substantiation view to be true. We should just take both forms of hierarchy as being on the table. One way you might do this is by using the topological hierarchy as kind of an add-on. So you might say, okay, well, maybe processing is serial and abstractive in modal cortices, and then it's more network-based or hierarchy centrality-based once unimodal processing is done. The problem with this is that it doesn't seem to incorporate the conflicting data that we showed you from V4. Another thing you might do is to rely on a kind of model-based pluralism, and this would be to say, look, there are different kinds of properties we might be interested in. So some people have suggested that the kind of thing that graph theoretical measurements explain are things like robustness properties, wiring optimality properties. So the graph theoretic project is not really a functional view. It's or at least not a view in terms of representational hierarchy. We might just keep both on the table. Similarly, you might try to suggest that the temporal modeling, even if it does follow Capalbo-et-al's results, doesn't actually question the representational hierarchy. You could tell a more complicated story. The worry about this is it may not incorporate the conflicting data either, because the data about V4 suggests that it's having a much more integrative role than the simple representational function that it's supposed to play on the traditional view. The other thing you might say is, well, the brain just implements a lot of different types of organization. So it might be that processing is serial and abstractive when you're just looking at a bottom-up stimulus. But it might be that perception in the context of action may require more dynamic interactions than just a simple feed-forward process. And moreover, action in the context of deliberation may require access to motivational and evaluative influences. So this would suggest that the type of organization we're looking for depends on the kind of behavioral context we're studying, and sometimes a simple processing hierarchy will work, and sometimes it won't. So we don't actually want to take a stand here in terms of which of these might be right, either the conflict view, the substantiation view, or one of the pluralist views. What we just want to stress is that these are all options that are on the table. One reason we want to stress this is it's very common in neuroscience to simply cite the traditional hierarchical view and employ it in new investigation. It's also very common in philosophy to cite neural hierarchies as evidence for some broad philosophical claim about the mind. Sometimes this is cited in discussion of cognitive penetration. Sometimes it's cited as a background organizational premise in discussion of predictive coding models. And what we want to just suggest is that all these moves are actually way too quick. It's unclear exactly how to understand the hierarchical organization of the brain. Are we over time? Should I cut off now, do you think?
We had 32 minutes according to my watch.
Oh, great, okay. Okay, cool. Well, I'll go through this last thing quite quick. So I think, or we think that the view you take on this matters for how you go about analyzing different functional organizations of the brain. So one test case that we're interested in is what's called the Rich Club. So in a Rich Club, what you do is you take all the connectivity you know, and you set a degree level K, and then you look at all of the areas that have a higher degree than K, and you just ask, out of all the possible connections between those areas, how many of those possible connections actually exist? If the areas that themselves are very high degree are also interconnected to each other, this suggests that this particular unit, which is called the Rich Club, is playing an extremely central integrative role in the network. Some have argued that the brain exhibits a Rich Club structure. Interestingly, many other organizations, including airports and gene regulation networks, also exhibit a Rich Club structure. But we think whether you take a traditional approach or a topological approach really makes a difference for how you analyze this. So on the traditional approach, since that these are the highest levels of the hierarchy, they should be representing the most abstract information, and they should be activated later in a task. According to a purely topological approach, you all just have to suggest that these areas might have a different temporal scale from other areas, but not that they need to represent abstract information. What's interesting about this is the Rich Club overlaps significantly with the default mode network, right? So how you think about the default mode network, especially as it overlaps with the Rich Club, changes quite a bit depending on which approach you take. And it actually looks like, at least there's some evidence that the substantiation view is not right for this. So the Rich Club works not just after perceptual information or before action. It actually works over a very extended time scale, what's called infraslow oscillation frequencies. And this influence mediates network organization across task changes. And one way that some researchers have described this is that the Rich Club mediates competitions between more specific information processing networks rather than representing highly abstract scenarios. And if this is the case, then we don't need to think about the representational function of the Rich Club as we would if we had a traditional view. We just need to think about its role in mediating competitions between task-specific networks. So we think which way you think about this makes a big difference for how you go about analyzing particular parts of the functional organization of the brain. Okay. So in conclusion, we have really modest aims in this paper. We just want to suggest that there is no obvious sense in which there is a unitary hierarchical organization in the brain. There's a lot of complexity here, and again, given how influential this perspectives, both in neuroscience and in empirically informed philosophy of mind, we think we need to think super hard about what the actual functional organization of the brain is that's being revealed. All right, so thanks.